altitude or height is defined based on the context in which it is used. As a general definition, altitude is a distance measurement, usually in the vertical or up direction, between a reference datum and a point or object. The reference datum also often varies according to the context. Although the term altitude is commonly used to mean the height above sea level of a location, in geography the term elevation is often preferred for this usage. Vertical distance measurements in the down direction are commonly referred to as depth. Altitude in aviation. In aviation, the term altitude can have several meanings, and is always qualified by either explicitly adding a modifier, or implicitly through the context of the communication. Parties exchanging altitude information must be clear which definition is being used. Aviation altitude is measured using either mean sea level or local ground level as the reference datum. Pressure altitude divided by 100 feet is the flight level, and is used above the transition altitude in the U.S., but may be as low as 3,000 feet in other jurisdictions. So when the altimeter reads 18,000 ft on the standard pressure setting, the aircraft is said to be at flight level 180. When flying at a flight level, the altimeter is always set to standard pressure. On the flight deck, the definitive instrument for measuring altitude is the pressure altimeter, which is an aneroid barometer with a front face indicating distance instead of atmospheric pressure. There are several types of aviation altitude. Indicated altitude is the reading on the altimeter when the altimeter is set to the local barometric pressure at mean sea level. Absolute altitude is the height of the aircraft above the terrain over which it is flying. Also referred to feet per meters above ground level. True altitude is the actual elevation above mean sea level. It is indicated altitude corrected for non-standard temperature and pressure. In UK aviation radio telephony usage, the vertical distance of a level, a point or an object considered as a point, measured from mean sea level. This is referred to over the radio as altitude. CQNH, height is the elevation above a ground reference point, commonly the terrain elevation. In UK aviation radio telephony usage, the vertical distance of a level, a point or an object considered as a point, measured from a specified datum. This is referred to over the radio as height, where the specified datum is the airfield elevation. Pressure altitude is the elevation above a standard datum air pressure plane. Pressure altitude and indicated altitude are the same when the altimeter is set to 29.92 inches Hg or 1013.25 millibars. Density altitude is the altitude corrected for non-ISA International Standard atmospheric conditions. Aircraft performance depends on density altitude, which is affected by barometric pressure, humidity and temperature. On a very hot day, density altitude at an airport may be so high as to preclude takeoff, particularly for helicopters or a heavily loaded aircraft. These types of altitude can be explained more simply as various ways of measuring the altitude: indicated altitude the altimeter reading, absolute altitude altitude in terms of the distance above the ground directly below, true altitude altitude in terms of elevation above sea level, height altitude in terms of the distance above a certain point, pressure altitude the air pressure in terms of altitude in the international standard atmosphere, density altitude the density of the air in terms of altitude in the international standard atmosphere. Altitude regions. The Earth's atmosphere is divided into several altitude regions. These regions start and finish at varying heights depending on season and distance from the poles. The altitudes stated below are averages: troposphere surface to 8,000 meters at the poles 18,000 meters at the equator, ending at the tropopause. Stratosphere troposphere to 50 kilometers, mesosphere stratosphere to 85 kilometers, thermosphere mesosphere to 675 kilometers, exosphere thermosphere to 10,000 kilometers. High altitude and low pressure regions on the Earth's surface that are high above mean sea level are referred to as high altitude. High altitude is sometimes defined to begin at 2,400 meters above sea level. At high altitude, atmospheric pressure is lower than that at sea level. This is due to two competing physical effects: gravity, which causes the air to be as close as possible to the ground. and the heat content of the air, which causes the molecules to bounce off each other and expand. Because of the lower pressure, the air expands as it rises, which causes it to cool. Thus, high-altitude air is cold, which causes a characteristic alpine climate. This climate dramatically affects the ecology at high altitude. Relation between temperature and altitude in Earth's atmosphere. The environmental lapse rate is the rate of decrease of temperature with altitude in the stationary atmosphere at a given time and location. As an average, the International Civil Aviation Organization defines an international standard atmosphere with a temperature lapse rate of 6.49 kelvins, a degree Celsius, /1000 m/1000 feet, from sea level to 11 kilometers. From 11 to 20 kilometers, the constant temperature is of 56.5 AA degree Celsius, which is the lowest assumed temperature in the ISA. The standard atmosphere contains no moisture. Unlike the idealized ISA, the temperature of the actual atmosphere does not always fall at a uniform rate with height. For example, there can be an inversion layer in which the temperature increases with height. Effects of high altitude on humans. Medicine recognizes that altitudes above 1,500 meters start to affect humans, and there is no record of humans living at extreme altitudes above 5,500 to 6,000 meters for more than 2 years. As the altitude increases, atmospheric pressure decreases, which affects humans by reducing the partial pressure of oxygen. The lack of oxygen above 2,400 meters can cause serious illnesses such as altitude sickness, high-altitude pulmonary edema, and high-altitude cerebral edema. The higher the altitude, the more likely are serious effects. The human body can adapt to high altitude by breathing faster, having a higher heart rate, and adjusting its blood chemistry. It can take days or weeks to adapt to high altitude. However, above 8,000 meters altitude acclimatization becomes impossible. There is a significantly lower overall mortality rate for permanent residents at higher altitudes. Additionally, there is a dose-response relationship between increasing elevation and decreasing obesity prevalence in the United States. In addition, the recent hypothesis suggests that high altitude could be protective against Alzheimer's disease via action of erythropoietin, a hormone released by kidney in response to hypoxia. However, people living at higher elevations have a statistically significant higher rate of suicide. The cause for the increased suicide risk is unknown so far. For athletes, high altitude produces two contradictory effects on performance. For explosive events, the reduction in atmospheric pressure signifies less atmospheric resistance, which generally results in improved athletic performance. For endurance events, the predominant effect is the reduction in oxygen, which generally reduces the athlete's performance at high altitude. Sports organizations acknowledge the effects of altitude on performance. The International Association of Athletic Federations, for example, marks record performances achieved at an altitude greater than 1,000 meters with the letter A. Athletes also can take advantage of altitude acclimatization to increase their performance. The same changes that help the body cope with high altitude increase performance back at sea level. These changes are the basis of altitude training, which forms an integral part of the training of athletes in a number of endurance sports including track and field, distance running, triathlon, cycling and swimming. Effect of high altitude on animals. Decreased oxygen availability and decreased temperature make life at high altitude challenging. Despite these environmental conditions, many species have been successfully adapted at high altitudes. Animals have developed physiological adaptations to enhance oxygen uptake and delivery to tissues, which can be used to sustain metabolism. The strategies used by animals to adapt to high altitude depend on their morphology and phylogeny. Fish at high altitudes may also have a lower metabolic rate, as has been shown in highland west slope cutthroat trout compared to introduced lowland rainbow trout in the Oldman River Basin. There is also a general trend of smaller body sizes and lower species richness at high altitudes observed in aquatic invertebrates, likely due to lower oxygen partial pressures. These factors may decrease productivity in high-altitude habitats, meaning there will be less energy available for consumption, growth, and activity, which provides an advantage to fish with lower metabolic demands. The naked carp from Lake Kangay, like other members of the carp family, can use gill remodeling to increase oxygen uptake in hypoxia. The response of naked carp to cold and low oxygen conditions seem to be at least partly mediated by hypoxia-inducible factor 1. It is unclear whether this is a common characteristic in other high-altitude dwelling fish or if gill remodeling and HIF1 use for cold adaptation are limited to carp. Rodents. Rodents living at high altitude include deer mice, guinea pigs and rats. As small mammals they face the challenge of maintaining body heat in cold temperatures, due to their large volume to surface area ratio. As oxygen is used as a source of metabolic heat production, the hypobaric hypoxia at high altitudes is problematic. There are a number of mechanisms that help them survive these harsh conditions, including altered genetics of the hemoglobin gene in guinea pigs and deer mice. Deer mice use a high percentage of fats as metabolic fuel at high altitude to retain carbohydrates for small bursts of energy. To convert fats to energy in the form of ATP, more oxygen is required than to convert the same amount of carbohydrates. The reason they use fats is believed to be because they have it in large stores, but also means that they must eat more or they will begin to lose weight. Other physiological changes that occur in rodents at high altitude include increased breathing rate and altered morphology of the lungs and heart, allowing more efficient gas exchange and delivery. Lungs of high-altitude mice are larger, with more capillaries, and hearts of mice and rats at high altitude have a heavier right ventricle, which pumps blood to the lungs. At high altitudes, some rodents even shift their thermal neutral zones so they may maintain normal basal metabolic rate at colder temperatures. Birds. Birds have been especially successful at living at high altitudes. In general, birds have physiological features that are advantageous for high-altitude flight. The respiratory system of birds moves oxygen across the pulmonary surface during both inhalation and exhalation, making it more efficient than that of mammals. In addition, the air circulates in one direction through the parabronchioles in the lungs. Parabronchioles are oriented perpendicular to the pulmonary arteries, forming a cross-current gas exchanger. This arrangement allows for more oxygen to be extracted compared to mammalian concurrent gas exchange. As oxygen diffuses down its concentration gradient and the air gradually becomes more deoxygenated, the pulmonary arteries are still able to extract oxygen. Birds also have a high capacity for oxygen delivery to the tissues because they have larger hearts and cardiac stroke volume compared to mammals of similar body size. Additionally, they have an increased vascularization in flight muscle due to increased branching of capillaries and small muscle fibers. These two features facilitate oxygen diffusion from the blood to muscle, allowing flight to be sustained during environmental hypoxia. Birds' hearts and brains, which are very sensitive to arterial hypoxia, are more vascularized compared to mammals. The bow-headed goose is an iconic high flyer that surmounts the Himalayas during migration, and serves as a model system for derived physiological adaptations for high-altitude flight. See also, List of capital cities by altitude, references. External links, Altitude Pressure Calculator. Apex. Retrieved August 8, 2006. The Race to the Stratosphere. U.S. Centennial of Flight Commission. Archived from the original on March 9, 2006. Retrieved January 25, 2006. Downloadable ETOPO2 Raw Data Database. Downloadable ETOPO5 Raw Data Database. Calculate true altitude with these JavaScript applications. Find the altitude of any place.